Let's begin. This is first thing first, because I guess the simulations and everything, it's kind of matrix thing. Is kind of gets it gets we inside an illusion, and we have be careful about that. The trick or the rule of thumb is don't forget the basics that is behind the curtains. No, all the answers is there. So this is some basics that I want to discuss with you, mainly with the people that is beginning. So structural modeling basics. You are a review on structure statics, a fast review, okay? I imagine that all of you already had a lecture or more than one. So I start with this question: why we do not make calculation by hand anymore? Don't we? So we stood at first the simple superbeing case with hand and computer responses to discuss about this question, and finite element modeling that Karamba is on it. Basic modeling setup, inputs and outputs. We won't discuss the mathematics and calculus that is behind the finite element, but it's important that we are aware about it. And the main concern is the setup, input and output to get responses. Some comments about structured material modeling also. So our question: why don't we make calculation by hand anymore? I bring to you some kind of dates, kind of history of the people that developed this knowledge. So mechanics, physics mechanics and differential calculus development, not only by these people, but mainly by Leonardo da Vinci, Galileo and Newton, with the basics and this knowledge. Look at this dates. Strength of materials development. Note this, that is a sequence here. Continuous sequence of building this knowledge, and it didn't exist computer as we know today in this time. So all the calculus was made by hand here until here. Not actually here, but almost here. And past the Second World War, the finite element method and computer-aided tools developed fast. So this is one of the authors. And in the 60s and the 70s, this development gets very fast. So here, this computer calculation, using this knowledge here. Okay, thank you. Hello, Chin. Hello, Henrique. You already started. So the difference between here and here is the complexity that you are mentioned. Complex calculation by hand is almost impossible for humans. So the computer brings it. And the planes, the airplanes at the war, look at the shape of the wings. When the finite element became, the shape start to change, because it was possible to make complex calculations. Okay, so the structured computer simulation and modeling provides precision and speed and afford complex shapes, calculations on complex shapes. By hand, the equations, it can only be solved in simpler geometries. This is the problem. Okay. The supercomputer simulation modeling provide complex access with similar level of difficulty in complex shapes or simple cases. Complex or simpler is the same difficulty for computer. It's not the same for us. However, we can't skip knowledge. We must comprehend the structural concepts or behavior and the models we build. So with these interfaces like Grasshopper and all of this interactive interface and our lives is very pushing forward. Everything is fast. We almost don't think what we are doing. So it's kind of dangerous on it. You have to be patient. You have to be careful about the geometry modeling, the consistency, the righteous product of the geometry. The geometry must be good and beautiful to the simulation, wherever the simulation is, works well, okay? The hand calculation can offer a way to validate or check our models. So when my structure model is giving me a response that I don't believe, or it's so strange for me, I can use the manual calculations to check the magnitude of the result. Okay, we cannot just believe what the simulation is giving to us. So let's do a comparison. This simple case of simple supported beam case with this model, very simple. This distributed load that can be its own self-weight or a load of a wall, for example. So the hand calculations with this statics, isostatics case, and the hand calculation is simply only on isostatical. You have this reactions, and let's consider that the load it has 20 kilonewtons per meter and a length of span of 5 meters, and we have these steps to do the calculation, and we have these reactions of oh my God, some strange noises is happening here, but okay. So we have the support reactions to do this calculation only for it. We can also calculate the displacement, and we are interested in the maximum displacement, the critical case. And we have this analytical expression that take into account the load, the span length, the elasticity constant of the material that the beam is made, and inertia. Considering cross-section properties from the dimensions of it, we can calculate this is elastic constant for concrete, the inertia calculations, and applying this expression, we have that this beam presents the maximum displacement of 0.3 approximately centimeter on the center of the span. So we have the displacement. The same for bending moment diagram. Actually, it's analytical expression. The shear force, that's for this case, this is equation. And we have this analytic handmade calculation results. For the internal forces and stresses, we can, from the bending moment, it has the top of the cross section, the maximum compression normal stress, and the maximum tension stress by this hand calculation. And for shear, similar for rectangular shape, our values. Look, all this time with a simpler case of a structure, all this calculation. With these critical results of stress and displacement, the structures are evaluated against the structural design codes. So the procedure to design structure is to get this displacement, stress, and so on, critical values, the maximum values, and the design codes get the rules to say if this pass the limits or not. And by hand calculation, traditionally, the design is a checking procedure. You have the situation like this example, and I see the design code. Let me see, do some little bit more hand calculation. It's okay, it passes. But we can discuss it a little bit with parametric approach. Nowadays, we could do a feedback loop, connecting these outputs with the design code rules to find the various structural model inputs. For example, spans and cross sections. This for architecture is kind of eliminates some steps and the design or the preliminary design, we can find the best spans, cross-sections, and materials for each structural system using parametric structural design, because we can close the loop of determine the critical values of the structure and face it against the design rule. We can close the loop and find the best values of my system, of my structural system. This is one of the greatest affordances of the structural parametric modeling. How would be the situation with an equivalent parametric model, Karamba, this simplest supported bin? We have that same diagrams of bending moment, of shear forces, of displacement. Here is my load, here is my beam model on Karamba. And I have automatically on time the maximum displacement. I have the maximum shear force, not the maximum only, but all the values numerically. I can have it graphically and numerically. Graphically, when we're doing an algorithm, it's not so useful anymore, because we have to do, it's better to do an automation. And automation is made by numbers, by list of values. We don't need anymore the graph, the diagrams. Diagrams is to do manually. So I can have all the results in a list. Shear forces and bending moments. Here is the value of this point, the value of this point, the maximum, and 0 again. The same for shear forces. And we have a lot of visually results. This is more updated, modern plot, modern view of the results than this. Okay, this distribution of stress on my member and the deformed shape. So red is compression, blue is tension, and white is no tension, no stress. And Karamba often use this unit, and it has this equivalency. So get note. Comparing the analytic solution, the hand calculation, and Karamba solution, it has very, very close or identical, because finite element modeling is an approximate method, but 2.3% it's almost the same. Below 5%, it's okay. Let's see the essential for modeling. Geometry as input. For bar models, beam, columns, bar trusses, bar element model has as geometry line segments. line segments, not polyline, not NURBS curve, line segments. If you have an arch, you have to break it in tiny line segments, okay? And mesh for shell elements. Shell is a superficial a shape of a structure that it has the same name for the formulation, the mathematical formulation of the structural model. So we use mesh, in this case, a polygonal mesh, okay? Cross-section shape and dimensions. You have to do this input. Material properties, in which is in form of constant values, is number that represent the elasticity property, and where it comes from. It comes from laboratorial measurements or design standard codes, these values, okay? And it's very common to use a linear model, linear and elastic, to design. Load types and values. We have point loads, we have line loads, we have superficial loads. Line loads and point loads. Line loads, it's very frequent to use in bar elements. Point loads is very frequent to act on point, on vertices. And superficial loads is very frequent to act on shell elements, shell members, like slabs, walls, and etc. Support types and its locations. You have to have supports on your structure. You have to inform it. Hinges, sometimes, it depends. And you must consider topological dimensions in meters on Karamba. Topological dimensions, the span dimensions, the length of the members. The geometry must be with meter magnitude. So you don't model a 5-meter beam length by 500 or 5,000. Okay, it's 5 meters, because the unit for computer doesn't exist. It only exists on our mind. We have to contextualize the unity. For computers, only numbers. So we have to care about the consistency of this unit dimensions, okay? And Karamba just works only with these topological dimensions in meters. The cross-section dimensions is centimeter, but it's more obvious, okay? Output, maximum displacement, because we have to design against design code with this parameter. Maximum displacement, maximum stress or acting forces and moments, buckling, susceptibility, support reactions to design the foundations. And let's start to model our sample, our example of supported beam, simple supported beam. We have start here with a point, a vertex in Grasshopper, move it with a move that's a cousin of copy. Copy and move, it's almost the same thing. And move using a vector, an x, global x, with a slide. So I have 2 points here. And using it as an input of a unique line segment. And we have this in the viewport. This point is it. This is another point. Is it, because it's a move, it's a copy. And we have 1, 2, 3, 4, 5 meters. That's our example solved. Okay. But the magic is this guy, because we don't have only this beam or this line segment. We have all the line segments length that this guy informs. And we discussed that in finite element modeling in Karamba, we can subdivide this line segment to do the same beam. And I explained about this. And if we divide this line segment, we have points. If we connect this point, we have a polyline. Polyline, it's not okay to model. So we break it and we have vertices again and segments. One segment, another segment, another segment, another segment. This is the same beam, but with 4 elements. Okay? Actually, it's not beam. Actually, it's still a geometry, but it's kind of virtually beam. And here we have the structure model inputs. We have line to beam. This line segments will be converted in elements, structural elements that will be used to do the calculations. So we have the geometry, we have the elements, the bar elements. So here we have bar elements. The points and the end of my beam will be model the supports. So we have a component that constructs or builds this support model. And we have translation and rotations on the global coordinate system, X, Y, and Z. So we can use plane as a coordinate system here. You know, if you don't enter anything here, they assume it will assume that it's the standard one. Okay. We have load online is the same component, and here you set if it's line load, if it's point load, if it's self-weight, and so on. And it works using vectors to inform the direction. Here with this asterisk, I can put an expression to minus x to indicate that it's upside down. And I can put a number or a unique number or a slide with a range of numbers. Cross-section is the same component on Karamba. Here, we can switch the type of this cross-section shape. Here is the rectangular because it's trapezoidal, but can be rectangular when you input the same number in upper width and lower width. It's rectangular, solid, for concrete or wood with this shape. And we have material constants. And here I pick some of the Brazilian concrete standard design code to calculate the elastic properties to input on the components that will be considered on the structural model. The standard one is steel. And if you put values, you can transform it for a different material modeling. So you have to pay attention in the design code, in the material design code that you are designing. If you are designing in timber, you have to take a look on the timber design code to how to calculate these constants. Okay, because timber, it has a lot of species and can you circular cross section? Yeah, circular. And if you switch here, you can change. Okay. Pay attention here in this asterisk, because the unit here in Brazil, we used to use MPa, but here is kilonewton per square centimeter. You have to just divide by 10 to convert from MPa to this unit. Okay. If I'm not wrong, you can also set as hollow or solid. Yes. It has another one that is rectangular, that's hollow. Okay. It is a trick. It has a trick to convert the solid circular. We will discuss about that further. We assemble. We have this components model assembly that get together all these inputs of elements, support, load, cross-section, material, joint that is hinges, to build the model, to assemble the model, the structural model. And it's, I don't know actually why this, but the trick, you have to do this to flatten all these inputs. Okay, sometimes if you don't do it, it gets some error. And we have a calculation engine or calculation engines. This is the static one. First, the first one, and you connect the assembled model to the stat calculation engine that does the calculation, and you can see the results in sequence. So I pick this model output here and connect on model inputs on components that brings me results, all kind of results, like support reaction, all of viewing features of the model, visual beam results like diagrams, or actual distribution, actual stress distribution, utilization, displacement, and so on. Okay. If you connect on this, not directly, you can view the format shape of stress distribution and displacement. Another results, that's numerical ones, that is the shear forces and bending moments. And displacement, translation, and rotations. How to extract results and transform it on performance indexes. We have the standard design codes specifying the limits for each design code, for each material. You have a limit of maximum displacement of each member. If you compare or do this ratio here between the maximum that is acting, that is occurring on the member, against the maximum allowable by the design code, you have an index. This is a displacement index that cannot be more than 1 or 100%. We have the demand here against the capacity here. Okay? And we have a limit of 100% of capacity of displacement. The design code doesn't allow that displacement is over a certain value. So you have this on an index, it's better. It's reached 100%, past 100%, it's 10%. That means what? That you are not using the whole capacity of the material. Okay? Or you can see the limitations of the structure system, looking at the design ratios. So we have the design ratio for displacement here to have an acceptable structure, a structure that is according to design rules. All the design ratio must be under 1 or under 100%. We have the same for normal stress and shear stress that we call utilization of the strength. And we can have it in another format, in the force and moments format. Steel and wood nowadays presents frequently in this form. So we have a design ratio for normal stress, design ratio for shear stress. And we can have a design ratio that informs the susceptibility of buckling. So we can look at this number and see the proximity of occurrence of buckling on the structure. And Karamba can give it to us. So I will pass by mail some Karamba codes to you, to your student. We have to discuss and help you to build an experiment in this workshop. And prepare this piece of code with this component that give to us numerical results. If it's numerical, we can make an automation. Okay. So Karamba gives to our util n. Util n is this ratio. Util m y is this. Util m z is this. Util v y is this. And it is here. So if we have this summation, we have the design ratio. Okay. And we are interested in the maximum. That is the critical. For normal stress and shear stress, we have similar thing about the displacement that is here. Okay. And buckling, but in this case, the beam, it doesn't has compression, and it's kind of error or no result. But with another examples that we discuss and work in this workshop, we have a result here. If I can make a list of the critical of each design ratio type, I can have the critical design ratio. In this case, the critical was normal displacement. Second place, normal stress. This is a characteristics of beam. Go in almost cases. The displacement is the critical. Second one, the normal stress. The third one, the shear stress. We call the normal values of loads in residential structures and everything. Okay. And it's good because what? The first design rule to be disregarded is displacement. So if any problem is occurring, like an overload, an incorrect use of the structure, more load than it was designed is acting, we can see the displacement or stop everything, get out of it. Okay, and it will be visible before to explode the design ratio of resistance, of strength. So we can have a window to avoid people to be on the structure. Every structure that has the design ratio critical displacement, it's a good thing, in my opinion. Okay. So here is that calculation. Here I rounded the value. Here I did the admissible displacement length 250 is the concrete design code. Here I do the calculation of the design ratio for displacement and consider here a creep index, the slow deformation of concrete, the simplified manner, considering that the maximum displacement is 3 times greater than the response of the model. Okay, and the buckling design ratio, you can get it inverting the buckling factor, that's this component of buckling that Karamba give to us. Okay, we have an index between 0 and 1, and if multiply by 100, we have between 0 and 100%. Okay. This is a simplified way to consider utilization for concrete and timber, because this calculation here is better fitted for steel and metals, or material that is more close to a linear behavior. That's not concrete and wood or bamboo. Okay, but all the books and design codes and everywhere using the linear model. That's it. So you have just to pay attention on material safety factors and creep. For wood, a simplified way is considered 2 times the maximum displacement that actually occurs in reality. So usually for design is used the elastic linear material model. Steel and other metals is well fitted by a elastic linear model, which means that the result that we get by the model is very close to the result in reality. If you build a similar beam and measure the displacement, for example, you have a very close result when we are talking about steel and metals. But reinforcing concrete is essentially a composite and non-linear material. So it has some gap, but it's not a new thing. We deal with it with some values that adjust this gap. We usually consider the maximum compression on concrete, and the reinforcement is designed after. Okay. It has to be careful with the creep effect on displacement. About timber, it's well fitted by a last linear model, but it has to consider the variation by humidity. You have to be careful with the design code material coefficient that will act on the elastic value. Okay. It has to be careful with the creep effect on displacement also. And parametric model on Karamba, where and how? We have this code that I will send to you. Okay. And this part is almost the same for everything. every example. That is the automation and post-processing of the results, the output of the model, structural model. And this part is the geometry modeling. Remember that example of the beam, the point that was copied, and the line. And we have another version. Okay, the magic, I will stop here. So it's okay. So it's very light. The magic is it. This is the magic of parametric. I have not only one instance of my beam. I have a lot of one. We actually model a typology, and we can parametrically have a lot of versions, a lot of instances of this typology. So transform the line on element, considering, taking account the vertices, to inform that we have the support in that points. And to be a simple supported beam, we have just to fix the translation, but we have to fix the rotation in X, because Karamba is a 3D modeling. And besides this is a 2D beam, the environment and 3D modeling. So if I don't fix in the rotation in X, we have a kind of problem here. The rigid body, because it's kind of this movement of the beam is occurring. So I have to fix this rotation in X. In this case, it is not an error, but it's a warning. And we have to be careful about this kind of, because the result is the same. We have results, okay? We have results, but sometimes this kind of inconsistency can lead to problems. So this is not Karamba. This is the basics of statics. Okay, so several times, a lot of problems is not problem of programming. It's not problem actually for modeling, but a problem of a consistency of the conception of the structural model. When I have a lot of hinges, this is more frequently, because when I'm using hinge, I can have a structural model or a structural system that is hypostatic. So do you understand when I say hypostatic? It doesn't have the minimal conditions of equilibrium. Okay. So if I do an input with a structural system model that doesn't have a minimal equilibrium, none of structural simulator will calculate it. The major problems lies on that, okay? So, we have, this is the magic. We have an on-time response on the formation and forces. And we can have a critical, let's copy it to here. So we can see the critical design ratio in this situation is 45.4%. If I can increase the span length, 5, 6, 6.4. It's almost the limit for this bin. Okay. This is the difference between the traditional ones, structural simulators, because traditionally we build the geometric model, set the constants, set the supports, set the loads, and play. We have a result. I don't want 5 meters length. I want 6.4. I have to rebuild the geometry and play again. It's kind of a static interface. Okay. So the difference here against the traditional one is this: we have an on-time response, changing the geometry or changing let's move to here, changing the cross-section, because if I increase the height, the critical design ratio it goes to below again. Okay. But the better part is not that for me. Is the feedback loop. If I connected the input with this, if I have a dynamic interface, I can connect this output of design ratio with the input to find the better input. And we can do this easily with Galapagos. How? I have to have this simple Grasshopper code. I think I can make it more. Is better now? Because I am interested only I'm only interested on the solutions that has design ratio, the critical design ratio below 100%, okay? So I have to penalize my fitness function. So if on your searching the best cross-section or the best span, if you have an instance that it has a design ratio that is above 100, you can penalize it, multiplying but a number. The fitness function, it gets a higher number. So in the minimization process of mass, for example, these instances that have a design ratio that is above 100%, it was penalized. It has a fitness function value that's higher. It will discard the generation per generation. So this is the rule of thumb. So I can use the Galapagos to search it. I can do it manually, like I'm showing here, but I can ask the computer to do this for me. So let's come back to the presentation. Optioneering. It's a concept that the first time that I saw it, it was an article by Dominic Rosa that says that you can view performances, view the performance of a certain system by numbers or by plots to view better the design space, the space of possibilities of that system. And we can write and build a table with this design space of our structure system. So it is useful to evaluate the structural system solution space using 2D plots relating pairs of parameters, and can be used to find best spans or cross-section types and values. So I can know or make a catalog of systems, not only structural system, but systems, building systems. So the frame is better with that material, with that kind of cross-section, is better in between, for example, 5 and 7 meters. The arch, it's better from this to this. Or this system is better with that kind of material, or on a material with that level of strength. Okay, I can view and make a catalog using optioneering. Visualize the relation between dimensions and material consumption. And optimization, it's a minimization or maximization a problem. And I will do it against one or more parameters. So it's a search. Here is kind of photograph or catalog of a system. And here is a procedure to search the best solutions of a system. Both can be used as tools to design. Okay. I can minimize I can minimize the material consumption or the cost, or maximize the span, or minimize the cross-section depth, for example. Okay. So in that code, we have this kind of components with TT2 box and a lunch box. I don't know if you have installed already. To store, to do the optioneering, to store a searching every instance, store in a table, store in a CSV file for further plot and see the characteristics of the system that I'm studying or designing, okay? And as I showed it to you, this little script of little Python script to select instances penalizing the fitness function. Okay. Here, storing valid modern instances, because when the design ratio is not under 100%, it penalizes the fitness function and retrieve new values here. So the non-valid instances is not stored. Okay. And here I'm writing it in CSV to plot and see where the system is better or not. So we have a kind of Excel table, and we can save on CSV because it's lighter than Excel file extension to read and write. Okay, it can be Excel also. And the result of plotting, we can relate span and mass rate of the beam. And we have the relation. Increase in this span, I have the increase in the mass. This point is only the valid solutions. The solutions, the instances that it has the design ratio below 100%. Okay, after running, we have the table, and we can make this plot. And we can analyze a little bit. Over 7.5, the lower bound, which means the minimum possibility of valid solutions, it has increased the inclination of this line. This is a signature of this beam. And ends here, my domain. I can go further. If I relate the span with cross-section height, is interesting because we have the range of the height, and we have what the books bring to us, the abacus, the valid region in the relation between span and cross-section height. Okay, to preliminary design. We don't have to do preliminary design if we use the parametric modeling. Okay, and we can see in this region of 8 meters span of this system that a value of cross-sectional height is 65 centimeters of a concrete beam. That it sounds familiar for this system. Okay, it's not incorrect to use 90 centimeters to achieve 12 meters of span length. Okay, but it has consequences. We have another relation, cross-sectional height against mass height, and we can see the relation is not linear. It's get steeper when I increase the cross section or the span. Okay. And span and strength of concrete. This lower bounds says to us something. 8 meters. We only can reach 8 meters long with 30 MPa of strength. We cannot reach with 20. We cannot reach 12, neither 20 or 30. Okay? So the optioneering is very good because we learn about the system. You cannot, you can skip to try to achieve 12 meters with 20 MPa of strength because you cannot reach it. Okay, this is a small sample, a small example to in a complex systems with a lot of more parameters that define the system. Imagine a truss that it has the height, it has the size of the bar, it has the overall shape. All these parameters can be a dimension that you can relate and see by plots the characteristics, the footprint, the signatures of the system, and know the system better. So this can avoid a lot of trying. So, okay. These values can be seen in an optioneering design framework. But if you ignore this part, only with the fitness function, we can, for a fixed span, try to get the better cross-section sizes by applying the optimization. Okay, it's the more traditional one. Or a second step after the optioneering analysis. Okay? So this is very important because if you are designing a structural truss, spatial truss, grid shell, or whatever, it has the question, which cross-section table will you use? Will you use aluminum? Will you use steel? Will you use timber? Taking account my architectural program. Okay, I can try all these options and see by optioneering which ones it's accountable in this process of design. Okay. In this case, the fitness function is the mass rate, and actually I changed using the mass rate and the critical design ratio because I want to maximize the design ratio considering below 100% and minimize the material consumption. Okay, let's do the two cases more complex. So I prepared a reinforced concrete vertical frame because it has some important hints when we have slab and beam. okay? And a steel grid shell with form find that we can use complex shapes. So reinforced concrete vertical frame. Again, is the same code with a little here and that, and there are some customizations, and I will send to you this code, okay? So you can study and bring discussions. And here's the difference. That is the modeling the geometry. So we have this block, the structural analysis, the structural analysis results, and structural design ratio calculations. Okay. So this is a structural frame example from grids. I picked the hexagonal one. Okay, and I can extract from the hexagonal grid the references, the geometry references, to build my geometry model that will be used as input of my structural model. So I pick the cells that is in polylines, break it, the vertices I use it to do the columns, and the segments I use to be the panels of the slabs. Okay, so the trick is using the mesh constructor from Karamba, because it considers some points on the mesh generation. Which point is it? The points, the endpoints, the vertices of the beams, because I have to have the coincident points of endpoints of beam and the points that the slab mesh in the contact of the beam. It has to be in the same place. This will guarantee that the deformation compatibility will occur between the slab and the beam. So this will guarantee that the slab is supported by the beam. Okay, if you doesn't do that, you will obtain the slab deformation different from the beam. This is not correct, and the result is not representative. Okay, and the trick is get the line, the entire line of the beam and break, and the points is included in the mesh generation of the slabs. Okay, and the segments I can use to be actually to the beam elements. Okay. Okay, and here is just the linear array to do the multiple floors vertically. So this is very important to have the bar and shell elements connected, and I call it finite element geometry. Okay, in a vertical linear array, I can multiply this single star to multiple stars, and we have some results. Deformations. You can see the column bending, because the bending of the floor system, the torsion of this beam, because the bending of the slab, We can see also the stress distribution. This is very expected, that this part is tensioning because this behavioral flexure and this compressing causes fixed on the ground. Okay. In the middle and the below part of the beam is tensioning. Okay. Another view that can be used to present the results, also to export to beam modeling, to face or collaborate in the building design with architecture and other systems. Another image, another view, and you can see the proportions. And design of a reinforced concrete structural frame on an X grid with flat slab over beams, considering a rigid frame, in this case, one floor with 5 meters beams. And we have these results. After running optimization, we have to achieve this with minimal consumption of material. That is very good. And we had this design ratios. And it's very interesting because the critical design ratio was the design ratio of displacement on slab. On beam, it's not even close to 100%. The normal stress on beam is not even close on 100%. The normal shear for slab also, and buckling also. So for this kind of system, in a majority of the cases, the critical, including for low rise frames, is displacement by flexure. If you increase the number of floors, this can change. Okay, so I will stop the share to open this code to show something. Here we have this result from Karamba, that code. Okay, here for beams, that it is in results. Okay, and for shell, all these components is here in, and it's not only one weight model, okay? But I guess it's a way to begin for who's is beginning. Cross sections, loads, and everything. Okay, the solver, the first order, the second order displacement, non-linear, and so on. So, as I said, we have in the same component all the kind of load switching. As I said, in the cross section, we can have tubular To do solid circular, you have to consider the thickness, the half, the diameter. It works. Okay. And material, we have some, I didn't use it orthotropical yet, but it has this option. Okay. In this modeling, I made for concrete of a floor system, slab and beams, one strength of concrete different from the columns. This is very common in real practice. Okay. So how I do that? I do by labels, because I have a slab label, beam label, and column label, and associate it in the line to beam that is from slab, from beams, not line to beam, smash to shell, line to beam from beams and column. Okay? Because I'm transforming geometry in elements and input these labels. So I use the same to avoid errors, labels to do. This geometry is slab, this cross section is for the slab, and this material is for slab and beam. And this load acting on slab. So I differentiate load, material, and cross-section by these labels. Okay? And load case by kind of label. This is load case 0. And if I consider wind, for example, I can use another load case with another label, 1, for example. So when I get the results, I can differentiate by these labels. In this case, I get only the slab results. In this case, I get only the gravitational, but I made another version with wind. That's more complex. And the programming, we have to filter and do some manipulations. So I have this one with wind. So I have a list, the gravitational, the self-weight is acting on 0, that's only gravitational. 1 load case, that is wind on X, and 2 wind on Y. So gravitational self-weight is acting in these 3 cases as the live load also, and the wall load and on the beams on form line also. But the wind load on facade on X is only in load case 1. Okay, so the results and the design ratios, I can select the result case 0. This is only gravitational ones. okay? And for beam. Using labels, I can select the members and the load cases to organize the results, okay? So here we have case 1 for beam, case 1 for column, case 1 for the slab. So I have design ratios, a greater collection now. Design ratio of displacement, horizontal and the top of the building. And when wind on X acting on wind on Y acting, beam displacement only, gravitational and slab displacement, and the design ratios. Beam normal stress design ratio only gravitational. Here for column and slab, and here with wind, it's a little bit different. It's 40.1 and 58.3 because it's more load, more demand for the structure. Okay. Let me see. Okay. Okay. So I will do. We can if we increase the span by 7. Oh, this is just a scale, okay? That you can put here without deformation. I increase the span and the design ratio gets hell over 100%. The slab displacement again, but the normal stress design ratio for beam exploded. So as column and just this. So I can use just a demonstration to minimize the concrete consumption and it's connected the strength of material, the cross-section sizes, and just it. I can put more things. In start. So it's very nice to see for me this changing because the genetic algorithm is searching. This is the first generation. And this avoid preliminary design by abacuses. We can have it more precisely and interacting with the space, architecture space that is designed. So it's a form finding approach that it's very close that what Rivka Oxman, for example, is saying, that you can integrate the disciplines and do a better collaboration framework on design process. Okay. So I can see the concrete consumption ratio. Okay. And it's very light and fast because it's not a huge model, but if it has 10 floors, the searching will be more slow. So besides this time of searching, it has more precise, more accurate than hand calculations and hand precise and preliminary design. In my point of view, the optioneering, it gets values there because you can prepare your office before designing situations. You can study some frequent, usual systems that you design often, and you can do optioneering study. And when the client comes, you already know which directions to go. Okay, so you can improve the design process actually, and this kind of it's kind of a cheat code on the experience, because if you have an experience of 30 years, you can already know what's the barrier span for that or this kind of structural system, for example. But you can maybe find some signatures that not obvious of each system doing non-optioneering. Okay, it's kind of extra work, but it's kind of investment on your design process and your office. Okay, or in a research also, because if you are studying, for example, a bamboo system, this system it's working well with this kind of bamboo. You can do optioneering and access this signature and have a collection of systems with signatures, and where you can see by plots where the system works better. Okay, I'll stop there. And it has to be more generations to have a better, but it already achieved a configuration that's below 100%. Okay, it's slab displacement again, but let's see. It's a slab of 17 centimeters that it was found. 33 by 59. You can round this, or programming, because 59 is not a good number to fabricate, right? And so on. And resistance 55, 79. Okay. Okay. The another one was a form find process for a rigid grid shell, and starting from here to here is the same, but these two blocks, it's to do the form find using Karamba. The modeling geometry, the funicular form finding, the structural analysis results, because I will get a form, a shape, as an input to structural analysis. So there's two steps, because this kind of form finding, a funicular form finding, is not a structural, actually, strength of materials and so on thing. Okay, it's a kind of equilibrium context. So this is a form find that the project plan geometry starts, because you can imagine that experiments of Gaudí, the hanging chain, and this code simulated it. So you start from a flat mesh where the edges of this mesh is the chains, and you put forces as weights in the hang chain, a physical experiment. So I have a project shape in the plan that we can visualize as a projected shape, that a project shape of a 3D shape that will be founded. Okay, so from this I convert or transform in a mesh. I can set the grid shell bar length, extract the edge support that I can fix, and we obtain bar axis, support vertices, and all vertices to apply the forces to do the form find. Okay, so this is the plan shape that I am picked for this example. So I have a mesh plan and select this curve to select this point to be fixed. Okay, and put force, and using this component that's in a simplified way performs a hanging chain funicular form find. Okay, so I use a unitary force and a very stiff cross section. It's kind of virtual. It doesn't have a real structural meaning, but we have in results lines in the form found shape, and we have, after this, performing a structural simulation and setting up a cross-section in a material over the shape, this result of displacement with colors indicating the magnitude of the displacement, or exaggerating the pattern of this deformation. Okay. Also the stress distribution, and we can see mainly actually for the arcs, the red color that indicates compression. Okay, a little bit of flexure here, and some handles to show the form found with the thickness of the bar that was designed. Okay, with design ratios, all design ratios below of 100%. Another view. is a rectangular tube, steel tube, and it has between 16 and 26 meters, 26 here, 16 here, okay? And it can be like this with vegetation or a cladding. In fact, it was designed with a cladding with 10 kilos per square meter weight. Okay, another handle to show the orientation of the bars, because the vertical local axis is orientated with the normal of the surface, okay? So we designed this with shell, 9 meters of maximum height, cladding with 10 kilos per square meter, using a rectangular steel tube catalog. So I consider that simplified way the wind acting and the displacement. In the case of wind acting, it is very common in this kind of structures. It was the critical design ratio case, okay? And you see more the material strength, the strength of material, more the critical will be displacement and stability that can be seen by buckling. Okay, because normal stress design ratio is very low, and it kind of in safety point of view, it can be seen as a good thing. Okay, the limit of broken is or instability is far from the limit. Okay, but the displacement that you can see, but it's not actually indicating that the structure will collapse. And construction rate is not so low. I use it with the birds, lunchbox, and TT tools. Okay, so when you open these codes, maybe it asks to install it. All of them is free, but I use it so to extract the mean size, because it's not the exact same size of the panel, and I extract the mean size to simplify a load, a wind load and a cladding load from influence area of the node. And this load was point load on the grid shell nodes. Okay. I use this block of code to extract the starting point of the bars and find the node list and the vector from the mesh. This is Weaverbird, the mesh from the lines found in the form find. To orientate because if I don't do this, we have kind of not actually good orientations. Okay, it's for fabrication, it will be a problem, and the response is completely different. right? It's interesting because this kind of structures, funicular one, it has a low or known bend moments, and you can see this 0.0 something bend moments. Here we have some 0.3, but it's very low moment. This actually should be 0 or 0 for every bar, but this solver that we use to do the form finding is not actually too accurate, but they can permit, they can allow a feedback loop because he is very light. To do the form find, it costs in my computer 401 milliseconds. The better you can do a form find using this solver, Newton Raphs, for example, or dynamic relaxation, is more accurate. The shape is, let's say, more funicular, so it has more a better performance to vanish the bending moments of the members. Okay, but it's okay for you that is beginning on this. Okay. I used also a CSV with a rectangular tool catalog, and with the lunchbox that I have a CSV reader that we have two columns and actually 3 columns, the 2 dimensions and the thickness, and it stored this table in a data tree. Each branch is a column, and in each branch we have a list with this column, and each item is a cross-section of the table. So instead of put a slider to define the cross-section dimensions, I use the CSV reader to pick from a catalog. So I can design with exactly the dimension that will be fabricated and so on. So I can feed the cross-section component from the catalog directly. Okay, and include in the optimization from the catalog. The thing is, it's not, it can be beyond the catalog, because it can be the table from your seller or what can I say? Seller is not seller. The people that can sell me the profiles, because usually they don't have the entire catalog. So you can fit the catalog and put in CSV and read from this. So you can work from the stock of the seller. Okay. So you choose, you design from where you will buy the product. So you can skip a lot of returning point on the design process. Let's see on the vertical frame with, I did something here also, is selecting points to apply wind load. because here is the nodes, you can see is green, the nodes that is acting the forces from wind in this direction, and this one another direction. Okay, so it's only a filter from the endpoints of the columns. Okay, it's another process that I have made here. So that's it. Questions before the break?